Oxidation of boron. So, we kind of sort of use a different guidelines to decide if a reaction involved an oxidation or a reduction than what we learned back in Gen Chem. In Gen Chem, we would figure out the oxidation states of everything on the reagent side. We figure out all the oxidation states on the product side. And then we'd see if they changed and how did they change, got more plus, got more minus, stuff like that. That's how we would assess, was there an oxidation or a reduction. And you can actually do that in organic reactions too. There's kind of a quicker, faster way to make that assessment without trying to figure out all the numbers and stuff like that. So what we do in general is, first of all, if we're oxidizing or we're reducing a molecule, what we're really talking about 99% of the time in organic chemistry, we're oxidizing some carbon on the molecule. There's a particular carbon, sometimes two carbons, that are getting oxidized. Okay, actually it could be more than two carbons, but in general, it's a particular carbon that's getting oxidized or reduced. Okay, and the way you can look at a carbon and decide if it's been oxidized or not, there are two tests that you can do, sort of visually look at it and do the test, and if either of them are a yes, then it's been oxidized. Okay. The first test is going from reagent to product. Does it have more bonds to oxygen? Doesn't matter if it's the same oxygen, different oxygen, blah, blah, blah. Does that carbon got more bonds to oxygen? If it does, that was an oxidation reaction. That's test one. The other test is, does it have less bonds to hydrogen? Okay? If it has less bonds to hydrogen in the product side versus the reagent side, some particular carbon, okay, then it was an oxidation reaction. You can use either of those tests. If either of them come up positive, then it was an oxidation reaction. Okay? And very frequently, both happen. Okay, that's the case today in our reaction. You get both more bonds to oxygen and fewer bonds to hydrogen. So let me write that down super quick. To decide if carbon been oxidized. Okay. Carbon gains more bonds to oxygen, okay? Or carbon loses bonds to hydrogen. Either one of those are true, then it was oxidation reaction. And by the way, reduction, which is the next reaction we'll do, I think it's next week. Reduction is opposites. By opposites, what I mean is that if you lose bonds to oxygen, it was reduced. If you gain bonds to hydrogen, it was reduced. Okay. All right. Before I forget, by the way, can't do that. I'm very dizzy. Before I forget, I have only gotten a few literature papers sent in to see if they're going to be appropriate. You guys got to get on that, please, because let's see. I haven't had to say no this year, but every once in a while I gotta say, hey, this ain't gonna work. This is a bad path. Don't go down this path. And then you got to get another one. So you know what I mean? Let's get this figured out. Let's get going on that process. It's not a hard process to do this. I know some people get nervous about doing public speaking and everything like that. But I'm not scary. Your classmates aren't scary. It's going to be fine. Everybody's going to be fine. Okay. But hang on just a sec. But and the process of doing the summaries and the glossaries and all that is a little time consuming. So let's get going on. Let's start moving. Yeah.
Do we have to dress professionally when we give our presentation? Okay.
I wear shorts every single day. I'd be the last person. Oh, really? That's a thing?
Yeah, so that's what I was asking.
I would like you in an evening gown.
No, thank you.
No. As long as I don't have to dress more professionally.
Sounds great.
All right.
Makes my life easier.
All right, so back to this. So we're doing an oxidation reaction. You know, maybe, I don't know how many years ago to say, 20, 30 years ago, almost all oxidations in organic chemistry were done with chromium reagents, or that was the majority of reactions were done with chromium reagents, and they work great. Reactions never fail, super good. Only problem is that the chromium reagents were super toxic. Okay? And, well, I don't know about super, but they were toxic nonetheless. And sometimes these reactions you got to do on a large scale. We're doing this in, you know, we're doing this in the teaching environment and stuff. So there was developed alternative reactions, and in particular, hypervalent iodines. What hypervalent means is it's an iodine with more bonds than it typically has. Okay? How many bonds does iodine normally have? Halogens? How many bonds does a halogen normally have? No. I think you're overthinking it, guys. When you were taught how to draw your Lewis dot structures, where do you put them? Do you put them in the middle of the structure? Things that you put in the middle are things that are going to have a lot of bonds. Or where do you put them? Normally they just have one bond, right? All they need is to share one set of electrons so that they get a complete octet. Okay? So typically they just have one bond, all the halogens. Okay? But because iodine is low enough on the periodic chart, it can use d orbitals, and they even have orbitals, and it can make more bonds than just the one. Okay, so, and if it makes those with something that's more electronegative, like oxygen, it itself, the iodine itself, becomes quite oxidized. Okay? All right, so I will explain and show you all about hypervalent iodines by showing you the reaction we're going to do today. There's two more needles coming down. By the way, so there's, I forget how they're distinguished by name, but there's this borneol, and then there's the borneol with the oxygen up. Okay, this is a little bit like a chair configuration, so you can sort of have an axial position and an equatorial position. And so there's another borneol with the equatorial position. When you look at your TLCs of that starting material, the stuff we bought from the chemical stores and stuff, you're going to see a big spot for your starting material, but you'll also see from the starting material a second little spot. You might be like, that's weird, this is stuff they bought. You know, why are there two compounds? Because it's naturally has an impurity of the other borneol. Okay? But nicely, both borneols, if they get oxidize to the same product. So it actually doesn't matter. Okay? All right. Our IBX reagent is our hypervalent iodide. So, yeah, look at this iodide. has 5 bonds to oxygen. Okay, oxygen is more electronegative. That means those bonds are not very equally shared. That iodide you can think of as being very depleted of electron density. Okay, so in essence, it is quite oxidized. Okay? Our product is camphor. Whether the oxygen's up here or the oxygen's down there, it doesn't matter in the product. It gets oxidized to that. Sorry. Shut off this noisy thing. And then the IBX, this is IBX. And it gets turned into this compound. Fewer bonds, now the iodide has fewer bonds to oxygen, so it was reduced, okay, while this was oxidized. All right, so let's check out the slick mechanism. Okay, so our IBX reagent. Our reagent itself can pick up a proton. Okay, when it does, it comes, I'm going to flip it around so that it's facing a better direction. Remember, molecules are not stuck to a whiteboard, they're floating all around, moving every which way. This iodide has a positive charge on it. It can get attacked by this lone pair. Kind of a technical method. Oh, this has a positive charge. We're going to have this proton, some base is going to come take it off, okay? And then it'll be off. And then one of these guys is going to get protonated by the solution. So basically a proton's going to fall off in one place and a proton's going to come on in another place. This is the one place it's sort of acceptable in the organic world to take a shortcut. And rather than show it coming off and then coming on, different structures, we're just going to do 2 arrows and say proton transfer. Okay, it's going to transfer to one of these guys. Oops, throw all kinds of stuff here. Structure's getting sloppier and sloppier. Okay, so this guy got protonated. It's got a positive charge on it now. And then see this? This is then sometimes referred as to a push-pull step. Okay, so essentially, this is now what I like to describe as sort of anchored water. It's a water molecule that's anchored onto the rest of this molecule. Okay, which makes it fantastic if it likes to leave, because if it leaves, it'll just be neutral, happy water. All right, so this guy can leave, but in actuality, it's probably more realistic to think of it getting pushed out like that. All right. So where are we now? Remember, you draw some curved arrows in a mechanism, and then you draw the intermediate. The intermediate is just whatever those curved arrows made happen. How do I want to flip this guy around? Okay. So rather than this double bond to this guy sticking down, I'm going to rotate so he sticks up. I got a good reason for that. Okay, almost there. Some base. Grab that dude. Okay. Let's redraw this stuff again. It's fun drawing pictures though, right? Just brutally ugly. Yeah, that's kind of a cool step. Every single oxidation, by the way, when you cover it in Dr. Morgan's class and stuff, and you're looking at the mechanisms of oxidation, okay? At some point in the mechanism, you're going to have an oxygen that has a leaving group on it, okay? Not an oxygen that's become part of a leaving group. You learned last semester that an alcohol can turn into a tosylate or a mesylate, a sulfonate leaving group. Okay? In those situations, that oxygen, he's going to leave too. This whole thing has become a leaving group. That's not what I'm talking about. In an oxidation reaction, at some point in the mechanism, the oxygen itself has a leaving group, and you're actually going to get, which is what's just like an E2 elimination that you learned, but you learned it with carbon. Okay, base is going to come down, grab that proton, you're going to get a double bond there, your leaving group is going to leave. Okay, and that's what's just about to happen here. Okay. Yes. That. Cool thing about this one is that the base, I'm not sure how they figured this out, but organic chemists, certain types of organic chemists love to do mechanism experiments where they sort of deduce what the mechanism must be. And what they've deduced is that the mechanism is intramolecular. It happens within the same molecule. The base is not a separate molecule that comes in and grabs a proton like you normally see in E2 elimination. The base is in the molecule itself. This huge molecule that we developed. So these electrons come here, grab that proton. Those electrons pop down there. Okay. This oxygen already has 4 bonds. Oxygen can't go hypervalent. So when those electrons come down there, the leaving group, okay, is this guy. This whole thing is that LG in enemies. Okay. And we're there. We've created the double bond here. We got rid of the H. And there's our product. Cool, right? Right on. Any questions, guys? When you start learning oxidation mechanisms and stuff in Dr. Morgan's class, look for this part of the mechanism. It's always there. All right. Okay. Cool. Here we go.